Hello again, this is Kyle Munyon on lesson 3-3, converse, inverse, and contrapositive of conditional statements. Here our learning targets are determine the truth value of these three things, converse, inverse, and contrapositive of conditional statements. So basically determine the validity of these new converse, inverse, contrapositive. We're also going to learn what a biconditional statement is here. So hopefully you've already done 3-2, you know what a conditional statement in the form if-then. Now that we know how to identify the hypothesis and conclusion, you can move those around and actually create what's called a converse, inverse, or contrapositive by either switching the hypothesis and conclusion. That's converse. You just flip the hypothesis and conclusion. By leaving the hypothesis and conclusion where they're at from the original conditional statement and negating them. By negate, I just mean saying the opposite of what it originally said. So if the original conditional statement said, if it is Thursday, then I wear a blue shirt, the negating that would be, if it is not Thursday, then I will not wear a blue shirt. So just the opposite of whatever the original conditional statement says. And a contrapositive, you do both flip and negate. So flip, we can abbreviate negate by not, and then for a contrapositive, you can do both, flip, not. So it's easy to remember the order, converse, inverse, contrapositive. We'll be using them a lot. And then you just need to also recognize for a converse flip, for an inverse not, and contrapositive you do both, you flip and negate, or flip not. So here we have a conditional statement. If a figure is a triangle, then it is a polygon. We know how to identify the hypothesis, and we know how to identify the conclusion. Once we've done that, it should be very easy to literally just switch. We do have the pronoun it here, and it's referring to the figure. So if I was to do anything where I switch the conclusion first, we wouldn't say it, we would just say a figure. So let's go ahead and try, see if we can write these statements and then determine if they're true, false as well. And if they're false, we can provide a counterexample. So the first one, if a figure is a triangle, then it is a polygon. If a figure is a triangle, we meet the hypothesis. We think of triangles. Are they all polygons? Yes. So true or false? This one's true because there aren't any counterexamples. If we can think of one, then it would be false, and we can give our counterexample. For the next one here, I'm going to write the converse of that conditional statement. If a figure is a triangle, then it is a polygon. So I'm going to take the hypothesis and the conclusion and switch them. So what was the conclusion is now going to be the hypothesis. So if a figure is a polygon, then it is a triangle. Okay, is that a true statement? So meet the hypothesis. If a figure is a polygon, think of any polygons, triangles, quadrilaterals, pentagons, hexagons, heptagons. Can you think of any that do not meet the conclusion of being a triangle? Yeah, any of the other ones that I listed. A quadrilateral is a good example. So this is false, and you could say a quadrilateral. Because that meets the criteria for the new hypothesis of the converse. If a figure is a polygon, it is a polygon, but it is not a triangle. So that is a counterexample. For inverse, we could take the original hypothesis and conclusion and leave them in the same spot, but negate them. So if the original conditional statement says, if a figure is a triangle, then it is a polygon, we leave the part about it being a triangle and the part about it being a polygon in the same spot, but we negate them. So if a figure is not a triangle, then it's not a polygon. Okay. So same thing, we need to think about some figures that are not triangles. So circle, rectangle, any quadrilaterals, pentagons, hexagons, all of those. then it is not a polygon. So can we think of some figures that meet the hypothesis of not being a triangle? So like a circle, rectangle, those are some good examples. Can we think of any that are polygons? So a rectangle is not a triangle, so it meets the hypothesis, but it is a polygon. So that is, we're trying to find figures that a counterexample meets the hypothesis but says the opposite of the conclusion. So this one is false because of a quadrilateral or a rectangle. I mean, a rectangle is a quadrilateral, but that's the one I said in the example. Because it meets the new hypothesis for this inverse, it's not a triangle, but it is a polygon. So it's the opposite of the conclusion. That's the counterexample that we came up with. Last one is contrapositive, and you just flip and negate, so it's a combination of a converse and inverse. We take the original conditional statement. If a figure is a triangle, then it is a polygon. We need to flip the hypothesis and conclusion, so now the part about it being a polygon comes first, the part about it being a triangle comes second, and negate. So if a figure is not a polygon, then it is not a triangle. All right, so on this one, now to test and see if it's true or not, we need to meet the hypothesis of this new contrapositive that we created. So we need to think of figures that are not polygons. So like three-dimensional figures or a circle is a good example. Let's see, test them out. Can we think of any that are a triangle? Well, definitely not, because if it's if we're trying to meet the conclusion and or find a counterexample that is a triangle, then obviously we can't find one that meets the hypothesis as well that is not a polygon. For us to end up meeting the conclusion or finding a counterexample for the conclusion, then we would have to have a triangle. So the only thing we could use that would meet the or make this a false statement would be a triangle. So we're obviously not going to be able to come up with any counterexamples. So this is actually a true statement because there aren't any counterexamples that we could come up with. All right, continuing on. A given conditional statement is true, the converse and inverse are not necessarily true. However, the contrapositive of a conditional is always true, and the contrapositive of a false conditional statement is always false. Likewise, the converse and inverse of conditional statements are either both true or both false. Statements with the same truth values are considered logically equivalent. Write a true conditional statement whose inverse is false. Okay, obviously you can make up whatever you want right here, but the inverse is one that you want to use the negating with. So P and Q stay in the same spot as the conditional statement. So our conditional statement is going to be if P, then Q. Our inverse is going to be if not P, then not Q. And I'm using these new little symbols right here, these wavy lines, to represent the negation of P and the negation of Q. So if not P, then not Q. All right, so I need to come up with a conditional statement that's true and then do the inverse and have it as false. Okay, so I guess we could keep going with shapes like we just did. If a figure is a square, then it has four sides, is a conditional statement, and that's true. If a figure is a square, then it has four sides. Obviously we know a square has four sides. That is true. So the inverse would be If a figure is not a square, then it does not have four sides. Okay, so my original statement, if a figure is a square, then it has four sides, is true. So we did that part. And when we write the inverse, if a figure is not a square, then it does not have four sides. Is this true or false? We're trying to have one that has an inverse that is false. Okay, so think of figures that are not squares, like circles, rectangles, stars, whatever. Is it possible to find one that is a counterexample, is to prove it false, that does have four sides? So a rectangle or any other quadrilateral, a trapezoid, if a figure is any shape that does have four sides, is a figure that's would meet, or the part that we need for the conclusion to be false, and any of them that have four sides that aren't squares will make this statement false. So a rectangle has four sides, and it's not a square, so that would be a good counterexample that proves this false. So if a figure is not a square, a rectangle, great, I've met the hypothesis. But a rectangle does have four sides, so that makes this a false inverse. All right, for number 3, write a true conditional statement that is logically equivalent to its converse. Okay, for number 3, it says write a true conditional statement that is logically equivalent to its converse. So obviously the converse has to be true as well for it to be logically equivalent, because they'll have the same truth values. So we just need a statement that when you do the converse, you switch the hypothesis and conclusion is also true. So let's use one that's not shapes now. If today is Monday, then tomorrow is Tuesday. That's a true statement. If today was Monday, which for most of you guys watching this on Monday was true, then tomorrow is Tuesday, regardless of what the actual day is today. The statement is true, because if today was Monday, then tomorrow would be Tuesday. The converse, all you need to do is switch the hypothesis and conclusion. So the part about tomorrow being Tuesday comes first. So if tomorrow is Tuesday, then today is Monday. So let me write these down just to make sure, those of you guys that need the visual. So here's my statement. If today is Monday, then tomorrow is Tuesday. The converse, all I need to do is switch these two parts right here. So now what was the hypothesis is now the conclusion, and what was the conclusion is now the hypothesis. So if I was to switch these for the converse, whoop, that's ugly, I would get if tomorrow is Tuesday, then today is Monday. And that's true as well. If tomorrow is Tuesday, that means today does have to be Monday. So here the original statement and the converse are both true. They are logically equivalent. All right, for our new vocabulary word, biconditional statement, it's just any statement that the original statement and the converse are both true is considered a biconditional statement. So the example we just did on number 3, if today is Monday, then tomorrow is Tuesday, that was true. The converse, if tomorrow is Tuesday, then today is Monday, is also true. That is a biconditional statement. All definitions that we learn can be written as biconditional statements. They can be written if and only if. So P if and only if Q. Write the definition of perpendicular lines in biconditional form. So we know that perpendicular lines are lines that intersect at 90 degrees. So we could say if lines are perpendicular, if and only if they intersect at 90 degrees. So I guess that's one way to write that one. Let me see if there's another way to write that one. We could also say two lines are perpendicular if and only if they form right angles or intersect at right angles. So let's go ahead and use that one. I'm just going to use the symbol for this one to throw it out there and to save some space. This upside down T symbol represents perpendicular. So two lines are perpendicular if and only if or 90 degrees, because that's what right angles mean. Consider the statement number 5. Numbers that do not end in 2 are not even. Rewrite the statement in if-then form and state whether it is true or not. So you could say if numbers do not end in 2, then they are not even. Okay, so now that we have it in if-then form, state whether or not this is true. So I know that a number that does not end in 2, so it could end in 3, 4, 5, 6, anything. So let's say like the number 13. Then it is not even. Well, that would be meeting the conclusion it's not even. So see if we can try some other ones. Obviously, try an even one like 14. It does not end in 2. But it is even, so that is a counter example. So this is false, because we can come up with a counter example. 14 does not end in 2, but it is even. And now it says write the contrapositive and state whether it is true or false. If false, give a counter example. So the converse would be switching the hypothesis and conclusion. If a number is not even, then it does not end in 2. That is the converse, and state whether it's true. So if a number is not even, think of numbers that are not even. Can you think of one that does end in 2? So to find a counterexample, we'd have to have a number that ends in 2 to find a counterexample, but also needs to meet the hypothesis of not being even. So think of numbers that are not even. 1, 3, 5, okay. What about some other numbers like, doesn't matter, decimals. We need to eventually find a number that, to be a counterexample that does end in 2. We don't have any of those. So there aren't any counterexamples. So this is true because there are no counterexamples. Write the inverse and state whether it's true. So inverse, we would leave the hypothesis and conclusion where they were at and negate them. So if a number does not end in 2, the negation of that would be if it does end in 2. I guess I could just make that ends in 2. then the original statement says, then it is not even. The inverse or negation of that part would be it is even. Okay, so if a number ends in 2, then it is even. That's true. And last one, write a contrapositive and state whether it's true or false or not. So if a number is even, then it does not end in 2. Then it does end in 2. It does. Yeah, the negation of not would be it does. So then okay, if a number is even, then it ends with 2. That is false because you can think of plenty of even numbers that do not end in 2. Counterexample would be 4. So that would be false. Okay. Can you write a biconditional statement for the original one? No. You can't, because the original statement and the converse are not both true. So although this one was true, the original one wasn't. To be biconditional, the original statement and the converse have to be true. So no, the original statement is not true. All right. Moving along, we now have a check your understanding section and practice. If you pause here, then when you start back up, I'll go over the check your understanding section, and then once I'm done with check your understanding, same thing, I'll have you guys pause here again and try the practice section, and then I'll go over the practice. All right, at this point you should have tried questions 6 through 10 on the check your understanding section. We're going to go over them. It says write 4 true conditional statements based on this biconditional. Okay, so based on this biconditional statement, we should be able to do these. Oh, there it goes. Takes a second to move. We should be able to do these 4 things right here, right? If P then Q, if Q then P. So that's all you're doing is taking the hypothesis and conclusion for in the biconditional statement. If and only if you have if P or P if and only if Q. So once you know your hypothesis and conclusion, you just fill in the blanks, literally plug in the hypothesis and conclusion wherever there's a P or a Q. What that looks like would be this right here. So you can look over check your answers for that one for number 6 right there. All right. For number 7, so the conditional statement is true and its inverse is false. What can you conclude about the converse and the contrapositive of the conditional statement? So for number 7, I would definitely suggest going back a couple pages to read what it says about when different parts of conditional statements are true or false. So if you have a true conditional statement, what you do or don't know about the converse, inverse, and contrapositive. So let's go and do that. Right now we have a conditional statement. I'm going to go ahead and mark all of these that we have: the conditional, the contrapositive, the inverse, and the converse was this one. I messed that up there. Let me fix it. The conditional statement, the converse, and the contrapositive. So if the conditional statement is true and its inverse is false, what can we conclude about the converse and the contrapositive of this conditional statement? Okay, so it looks like at the top of this page it tells us some information. If a given conditional statement is true, the converse and inverse are not necessarily true. However, the contrapositive of a true conditional statement is always true. So I know that the contrapositive of a true conditional statement is always true. I know for sure that this is true. What else does it say here? And the contrapositive of a false conditional statement is always false. Likewise, the converse and inverse of a conditional statement are either both true or both false. So whatever the converse is, the inverse has to be, or whatever the inverse is, the converse has to be. So here I know that the inverse is false, so the converse also has to be false. So for number 7, based on the information it gave us about the conditional statement being true and the inverse being false, because the conditional statement is true, I know the contrapositive has to be true. Because the inverse is false, I know the converse has to be false as well. Basically, the first and last ones have to be the same, and the ones in the middle have to be the same. All right, number 8. Are these two conditional statements logically equivalent? Explain. Basically, do they have the same truth value? If a polygon is a square, then it is a quadrilateral. That is a true statement. If a polygon is a square, it's got 4 sides, it is a quadrilateral. The next one, if a polygon is a quadrilateral, then it is a square. That is not true, because there are other quadrilaterals that don't have to be squares. So like a rectangle, it's quadrilateral, but it's not a square, so false. So these are not logically equivalent. Explain. The reasoning is because they don't have the same truth value. For number 9, Toby says that the converse of the following statement is true. Is Toby's reasoning correct? And explain. If a number is divisible by 6, then it is divisible by 2. Okay, so that original statement is true, because numbers divisible by 6, like 6, 12, 18, 24, all of those are divisible by 2. But the converse would switch the hypothesis and conclusion, and the converse would say, if a number is divisible by 2, then it is also divisible by 6. So think of numbers that are divisible by 2, 2, 4, 6, 8, 10. Are all of those divisible by 6? No. Obviously we can provide a counter example. So is Toby's reasoning correct? No, because a counter example to that statement would be like 4. A counter example for the converse. All right. Consider the last statement for number 10. All birds have wings. Write this statement as a conditional statement. If an animal is a bird, then it has wings. Can you write this statement as a biconditional statement? Well, if the converse was also true, then well, the original statement, all birds have wings, that's true. If an animal is a bird, it does have, I guess there might be a specific example of someone. Who cares? For the most part, all birds have wings are true. The converse, though, for it to be a biconditional statement, the original statement and the converse both have to be true. The converse would be if an animal has wings, then it is a bird. So a butterfly, does it have wings? Yes, you've met the hypothesis. Is it a bird? No. So a butterfly would be a counterexample, making the converse false. So then it cannot be written as a biconditional statement. No, because the converse is false. All right, now we can take a moment and go through the lesson practice for 3-3. Basically the exact same thing you were doing. Pause here, and we'll pick up in just a moment. All right, now that you've had some time to go through these questions, let's check our answers. Here we have a conditional statement, right? The converse, let's go ahead and do that. If a vehicle has 4 wheels, then it is a car. So it is referring to the car. Whoops. We should be able to do each one of these here. Right, so converse is if Q, then P. So I'm just going to flip the hypothesis and conclusion. I'm going to even make this summary a little bit shorter. Whoops. For the converse, it's Q, then P. All right, so if a vehicle is a car, then it has 4 wheels. All right, so the inverse is the hypothesis and conclusions stay in the same spot, but they are negated. Oops. So if not P, then not Q. So if a vehicle does not have 4 wheels, then it is not a car. And the contrapositive, you need to flip and negate. So negate Q, then negate P. So I'm just going to say this one. I'm not going to write it because we're running out of room. But if a vehicle is not a car, then it does not have 4 wheels, would be the contrapositive of this one. All right, for number 14 says, write the definition of the vertex of an angle as a biconditional statement. Okay, so we know a vertex to be the point, the common endpoint of 2 rays created. So we could say that a point is the vertex of an angle if and only if is how we write biconditional statements. So a point is the vertex of an angle if and only if it is the common endpoint of the 2 rays that create the angle. So a point of the 2 rays that make the angle. All right, for number 15, give an example of a true statement that has a false converse. Okay, you could have come up with whatever you want, but I'll keep an easy non-geometry example. If it is raining, then the grass is wet. That is a true statement. If it's raining right now outside, the grass would be wet in front of my house. The converse, though, would be if the grass is wet, then it is raining. Does not have to be true. Obviously, it could have just rained. Maybe the sprinklers came on. Could be multiple reasons that we could use as a counter example for that one. So anything that when you switch that hypothesis and conclusion and then it becomes a false statement would work for that. Number 16, given if x is blue, then y is gold, and 2y is not gold, which of the following must be true? Okay, well, this one's pretty easy. We know that y is not gold, so the only way that we know y would have been gold is if x was blue. So we know that x is not blue. I know that for sure, because if x was blue, then y would be gold, and y is not gold. Oh, okay, so it looks like we're done here with activity 3. You should now be prepared to do the homework from your homework calendar. these are the questions that you should be going over. If you have questions from the Activity 3 section here, these are ones that you can go over at 7:30 in your Zoom class meeting. So make sure that you make it to those and have your questions ready to go so you can address these. Generally, I think they just provide answers. You can check your work, is what I do. And then if you check your work and have some questions, or just knew already you didn't know how to do something, that's the time that you'll go over those. All right, see you guys next time.